Work, energy, and power is our next discussion in engineering physics. In contrast with the general definition of work, such as working out when you mean exercising, studying as a means to work your brains out, doing a job as some sort of work, or even cleaning as a form of household work, physics defines work differently. In physics, work is the amount of energy put on an object to move it a certain distance. From this definition, the force and the distance should be moving coincidentally in one direction. So far in the course, we have been talking about forces. For a physicist, to understand work, he has to have a solid background of forces. To elaborate on the definition, let us take a particle, in this case a crate, which is pulled or pushed as a certain direction. Take note that the force should be parallel to the direction or movement, so both the push and the pull are considered the force, and the distance traveled by the particle will be the distance. In formula, work is computed as force by distance, or that would be W is equal to F times T. And in units, force is taken as newtons, distance as meters, and Newton meters is what we call joules. In this next case, having a string tied to the particle, the exerted force will be inclined at a certain level, but the particle will move in a different direction. In order to solve for work, the direction of the movement is followed. Thus, the formula of work will then be integrating the x component of the force, which is actually the force parallel to the particle's motion. And by component method, we can solve for f sub x as f cosine of theta. So plugging the new parameter for work, it would then be f cosine of theta multiplied by d, whereby taking the instantaneous amount of work done at a certain point, we are just to have the integral of the formula making it. Talking about instantaneous work, most of the time the force or strength of pull will change as the individual gets tired. So in the computation for work done by varying force, we use the integrated equation, and by simplifying it, we get W is equal to half of F multiplied by x squared with our upper and lower limits as x sub 2 and x sub 1, which can then be further simplified into W is equal to half of F multiplied by x squared. A classic example of work using varied force is the spring, having the formula W is equal to half of K times x squared, where K is taken as force constant of the spring and X would be the maximum elongation or compression. The next term to keep in mind is energy, which is defined as the capacity to do work. As these two definitions just interchange, the unit for energy is similar with work, joules. There are two general kinds of energy. One we call the kinetic energy, or that which involves motion. Thus, the equation includes velocity, which is kinetic energy is equal to half of mass times the square of velocity. That would be Ke is equal to 1/2 m times v squared. The other type is potential energy, and from its name, this is a stored energy just waiting to be released. One common type of potential energy is the gravitational potential energy. This type has been conceptualized with the idea that gravity exists. So let's take a car for example. If the car is suspended at a certain height, it has potential energy waiting to be released. That energy is computed from the pull of gravity, which then requires the car's weight. If the car is released, then there is that energy created. So from F times T, the gravitational potential energy is computed as its weight or mass by gravitational acceleration multiplied by its height. Some references use PE for potential energy while others use U. It is up to you what you find convenient. The other kind of potential energy is with springs known as the elastic potential energy. At the first illustration, the spring is in equilibrium as there isn't any force applied. Upon the introduction of a force from a mass m to a distance x, and the mass was just constantly applied, the spring gathers potential energy which is equal to half of kx squared. And because it isn't at work yet, Ke is taken as 0. In the third image, the mass is released and the spring started working. Thus, the potential energy was converted into kinetic energy, which is computed as half of mv squared. How do we correlate work with energy? It is through a theorem known as work-energy theorem. This concept believes that the net work is just the difference of energy. So, by expanding both terms, net work is simply the net force by the distance traversed, and change in energy is taken as final less initial kinetic energy. Take note that energy is computed as the summation of both kinetic and potential energy. The law of conservation of energy states that energy can neither be created nor destroyed. It may only be transformed, which would mean the same discussion previously, that the total amount of work done is equal to the change in total energy. The next parameter is power. Power is simply defined as the amount of work done at a specified time, so the formula is work all over time, or force times distance all over time. We all know that d all over t is also velocity, so we can transform power in terms of velocity as force times velocity. In SI units, power is taken as watts, and in imperial unit system, it is pounds-foot per second. When converting, you can say 1 horsepower is 746 watts or 550 pounds-foot per second. Let's have an example for work. A crate weighing 50 kilograms is pulled up a plane of 15 degrees inclination by a force F, which is equal to 200 newtons acting parallel to the plane. The crate has a coefficient of friction to the surface as 0.15. If the block travels 12 meters along the incline, determine the following. A. Work done by the force F. B. Work done by the gravitational force. C. Work done by the normal force. D. Work done by the frictional force. And E. Total work done on the crate. Drawing the FBD of all the forces in the particle, we have the applied force, that would be F, is equal to 200 newtons, drawn as specified in the problem. The particle weight is also present, which is always directed vertically downwards. Next is the normal force acting with the weight, but take note that the normal force is always perpendicular to the surface. And lastly is the frictional force, taking the opposite direction with the movement. As discussed, frictional force is solved through normal force by multiplying it with its coefficient of friction. The first requirement is to solve for the work done by the applied force F. So by focusing on the applied force alone, the FBD will be as follows. The 200 Newton force is acting parallel to the movement of the crate. So we can readily use the formula work is equal to force times distance. And that is force of 200 newtons multiplied by 12 meters distance, giving us 2,400 joules. The next requirement is to determine the work done by the gravitational force or simply the particle's weight. Let's focus on that force only. By having the weight vertically applied while the particle is inclined, we are supposed to get the weight's component, which is parallel to the motion. Let us create an inclined axis we call x prime y prime axis. If we denote the axis parallel to the surface as x prime, then the component we are looking for is wx prime. Reflect the inclination of the surface to the particle, making it refer to the y prime axis. And again, from previous discussion in vectors, we can find wx prime as the weight w multiplied by sine of the angle, or 15 degrees. So work as F times D will be w sine 15 degrees times t. And plugging in the digits, we have 50 times 9.8 sine of 15 degrees multiplied by 12, or 1,521.86 joules. The third question is work done by the normal force. As explained earlier, normal force is always perpendicular to the surface and it is a reaction to the particle's weight. So, to be able to determine normal force, we should take the y prime component of the weight. In this case, wy prime is taken as the weight multiplied by cosine its angle, or 50 times 9.8 cosine 15 degrees, which is equal to 473.3 newtons. By using the work equation as F times D, we can say that the force is perpendicular to motion, making it 0. Thus, work done by the normal force is also 0. Letter D is the work done by the frictional force. The formula for frictional force depends on the normal force, which we have solved earlier. So frictional force is mu by normal force, which is 0.15 multiplied by 473.3 newtons. The frictional force is acting parallel to the surface, so we would simply multiply it with a distance of 12 meters from our work equation to arrive at 0.15 times 473.3 multiplied by the distance of 12 meters, coming up as 851.94 joules. The last requirement is to determine the total work done, which is just taking the net force and multiply it with the distance d. That would be F with Wx prime and the frictional force F with the distance d. So, our formula would turn out as F less Wx prime less our frictional force F and everything multiplied by d, which would be 200 less quantity of 50 times 9.8 sine 15 degrees and less the quantity of 0.15 times 473.3, where everything would be multiplied by 12, or simply 144.17 newtons times 12 meters, which would give us 26.20 joules. As the formula is just the summation of work done by each individual force, we can compute for total work as the work done by the applied force with that of the weight, normal force, and frictional force, which should give the same answer. Let's take an example for energy. A 1.5 kilogram book is sliding along a rough horizontal surface. At point A, it is moving at 3.21 meters per second, and at point B, it has slowed to 1.25 meters per second. A. How much work was done on the book between A and B? And B. If work of negative 0.75 joules is done on the book from B to C, how fast is it moving at point C? And C. How fast would it be moving at C if work of positive 0.75 joules were done on it from B to C? Illustrating the situation, we have a book of 1.5 kilograms sliding to a horizontal surface where, at point A, it has a velocity of 3.21 meters per second, and at point B, it slowed down to 1.25 meters per second. Requirement A is asking for the work done on the book between A and B. And with the velocities given, we can solve for the kinetic energy, such as, at point A, Ke is equal to half of 1.5 times 3.21 squared, which would give us 7.73 joules. And at point B, half of 1.5 times 1.25 squared would give us 1.17 joules. But how do we convert energy into work? We use the work energy theorem, stating that the network is just the relative kinetic energy. So, work net is equal to 1.17 less 7.73, giving us the answer of negative 6.56 joules. For letter B, with the incorporation of point C, where the net work from point B to C is given as negative 0.75 joules, compute for the velocity of the book at point C. By using the work energy theorem again, we can solve for the net work by W net is equal to half of mv sub c squared less kinetic energy, which was solved at point B. And simply placing our given, negative 0.75 is equal to half of 1.5 times v squared less 1.17 joules, which is simplified as 0.75 meters per second. Similarly, requirement C has a positive value for work. Thus, with the same work energy equation, we get 0.75 is equal to half of 1.5 times v sub c squared less 1.17. And the velocity of the book at point C becomes 1.6 meters per second. Check the next module on impulse and momentum.